America's space station, Skylab, afforded scientists the world over their first large-scale opportunity to conduct experiments in the weightless vacuum of space. One series of demonstrations explored the sometimes mysterious, often useful, but always fascinating phenomenon of magnetism. I'm Owen Garriott, the scientist pilot for the second manned mission to Skylab. While living aboard the space station, we had an opportunity to perform several interesting demonstrations of magnetic effects. But before we see these, let's look at some more familiar applications. Magnetism works in our homes for holding and closing things. In the doorbell, and in every electric motor and generator. Automobiles are full of magnets. Computers use magnetic cores in their memory banks. In fact, magnetic effects are woven into the very fabric of our technological society. Sometimes large electromagnets are used to move tons of metal. And much smaller ones are even used to record my voice, which you hear now. Today, the compass is perhaps the most familiar of all applications of magnetism. But 1,000 years ago, it was the only application, and magnetism was highly mysterious. By the early part of this century, the role of magnetic forces in nature had been understood, both experimentally and in precise mathematical terms. All magnetism depends on the flow of electric currents, whether on atomic dimensions or as large as the coils of a huge fusion test device in which plasma is contained magnetically and heated to millions of degrees. In today's avalanche of scientific and technical wonders, we may have forgotten a childhood fascination with magnets. My own memory was refreshed by some demonstrations with magnets in weightless conditions in the zero-gravity environment of the orbiting Skylab space station. I'd like to show you just how magnets behave in the freedom of zero-G, and why their motion can resemble that of a simple pendulum. First, a little review. Permanent magnets, like this compass needle, behave as if they had two strong poles, called north and south. Opposite poles attract, and like ones repel each other, as we can see in this demonstration. Now, an electromagnet affects the compass in the same way, but its magnetic field is produced by an electric current flowing in a wire coil, as we can see when I close this electrical circuit. The field of a permanent magnet, like this one, is also caused by electric currents, in this case due to the spin and orbital motion of electrons. In materials like iron, these atomic currents can be lined up by an external magnetic field, and then it will remain aligned for a long time after the external field is removed. The Earth is also a magnet with north and south magnetic poles. The explanation of terrestrial magnetism seems to require a dynamo effect driven by the rotation of the Earth. The experts still don't understand exactly how electric currents in the Earth's core generate its magnetic field, but the measured pattern resembles that of a giant bar magnet located at the center of the Earth. But the magnetic field strength at the Earth's surface is thousands of times weaker than that near strong magnets. Nevertheless, the Earth's magnetism can easily influence a delicately suspended compass, or these magnets that we see floating on the water. When I turn a compass away from the north-south direction, the Earth's field twists it back. In other words, the Earth's field exerts a torque on a magnet to align it. But since the compass needle swings freely, it first overshoots and then oscillates until friction damps out the motion. This bar magnet, hanging by a thread, can act the same way, just like a magnetic pendulum. And now you may begin to understand the behavior of magnets in Skylab. Here we have an ordinary pendulum. No magnet, just gravity tugging on it, producing a torque which tends to restore the pendulum to its equilibrium or rest position, aligned with the Earth's gravitational field. Magnetic torque performs the same function for the magnetic pendulum. You may know that a longer pendulum swings more slowly. To be precise, the swing period varies as the square root of the length, as shown by this equation. The magnetic pendulum has an equation with the same form. It will swing more slowly if it has a larger moment of inertia. That is, if the magnet is longer or heavier. On the other hand, the more strongly it is magnetized, the faster it swings, because the Earth's field, B, will exert a stronger torque on it. Suppose we conduct some of these demonstrations in the weightless conditions of space. We can't show a simple pendulum because the effects of gravity cannot be experienced when the spacecraft is in a freely falling condition. Magnetic effects were apparent because the Earth's field extends far out into space, well beyond the 270-mile altitude of Skylab. But as Skylab moves in its orbit around the Earth, its orientation to the magnetic field slowly changes. Let's watch the TV transmission from Skylab for a few minutes.
Here's a group of little magnets that I have. These are about 2 inches long and about 2/10 of an inch in diameter. And when we put these just floating out in midair, like I'm doing here, you can see that they take on a very definite orientation. For example, there is one. I've released it right out in the center now, and you can see it is settling down to a specific orientation. That's the direction in which the Earth's magnetic field is running here, right along parallel to this little bar magnet. And we can, of course, use this to determine the direction of the Earth's field right up here at the location Skylab is at. Now, as we travel around the Earth, if we could watch this for a longer period, we would see this little magnet make several rotations as we circle the Earth, because the direction of the Earth's magnetic field is changing. Now, here's another thing that we can do. You see, we must not get too close to it with another magnet, because when we do, the two of them interact, and they very much perturb and influence the other one. Now, let me just make a couple other little demonstrations here for you. First of all, we found, you see, that one magnet aligns very nicely with the Earth's field. And if you watch very carefully, you can see this dipole oscillate back and forth. And I'm removing all the other magnets so that they do not influence it. Now, perhaps you'd find interesting in one of your science classes to try to compute the period of that little compass. Or another way to do it, you can measure the period from this oscillation and compute the strength of the Earth's magnetic field right up here at the Skylab orbit. To do it, you'll need to know a little bit about this magnet, but you can estimate that approximately from the fact that it's a 2-inch long, 2/10-inch diameter magnet, and make a calculation to determine what the period of that oscillation should be. Now, here's another little question that might be appropriate for some of the younger members of our audience. Suppose I take two of these magnets and I put them together like this. Now, if I put these out here and let them float, you see they have almost no tendency at all to line up with the Earth's field. There's just a little bit remaining, but almost no tendency at all. And so perhaps you can explain that, or if you can't, you can ask your science teacher, and he or she can tell you why it is with two magnets like this, we seem to lose that tendency to line up with the Earth's field.
Before we see our next demonstration performed on Skylab, I'd like to show you how to measure the period of an oscillation, of either our magnet or of the pendulum. To start with, I'll give our magnet a small oscillation, and to time it, I'll wait until the motion is at one extreme and then start my stopwatch. We'll time 1 or even 2 or 3 periods, and when it reaches the other extreme again, I stop the watch, and that was just exactly 8.1 seconds. And when I divide 3 into this number, it gives 2.7 seconds for the period of each oscillation. You can use this technique to measure the period of any oscillating object, including our magnets in space. To make it a little easier, we'll mark the extremes of motion with a red flash in the next scenes.
Well, we saw the period of one oscillation a minute ago. Let me try it with 2 magnets, end to end like this. Now you see, they also oscillate. It's not like the 2 side by side. 2 end to end will still oscillate. And maybe you can see that. And you can measure this period. And from that period, you could again calculate the Earth's field, or you can determine something about the inertias of these combination of 2 magnets. And I'll leave that for another calculation for your science class. Now we'll give you a close-up look at the oscillation of one magnet. Put it back in the center. And now we'll use 2 to oscillate. And you see the period of this oscillation is a good deal more slow when we have 2 of them together. Now if I put 3 side by side, we again see they'll have a different period. Yeah, they move a little too fast there. There we go.
Now in another demonstration, we will observe the effect of a magnet attached to a nut, similar to this one, which we caused to spin like a top in space. Now I'm going to tape this magnet to the top of the nut with a piece of gray tape, just like we used in Skylab, and we'll observe the effect of this magnet on the spinning of the nut. We'll want to keep in mind that in this case, the polarity of this magnet is such that one face is a north pole and the opposite face of the magnet is a south pole.
But the next thing I want to show is when I tip these in a direction perpendicular to that. If it's not spinning, watch what it does. You see it spins right over and turns parallel to the Earth's field so that its spin axis, or its axis through the disk, is oriented with the Earth's field just the way it was before. That's its normal tendency, is to tip right over and align its own dipole with the direction of the Earth's field. Now I'm going to spin it about this direction, and we'll see what its reaction is. All right, now it's more or less spin axis perpendicular to the Earth's field at this point. And we may have to watch it for just a minute here, but the thing that I want you to observe is the fact that its spin axis is tipping over in another direction. You see, now it's now tipped over to the point where it's almost facing the camera. And now it has. It's tipped about 90 degrees, but not toward the Earth's field, which is off to my right. Instead, it is tipped over towards the camera. Now, this is called precession.
Now I'd like to show you a few of the more unusual effects of the Earth's magnetic field. Giant eruptions on the sun throw out clouds of electrically charged gas particles. They traverse the solar corona in a few hours and cross the 93 million miles to Earth in several days. Near the Earth, some of them are accelerated and then guided by the Earth's magnetic field into our polar regions. The particles funnel down into the upper atmosphere, where they excite neutral atoms and molecules, producing the visible lights known as aurora. A number of fine auroral displays were photographed from Skylab, starting about 2.5 days after a large flare on the sun. Higher energy charged particles also reach the Earth's upper atmosphere, Here they collide with air molecules, and their energy is transferred to new kinds of particles. They come not only from the sun, but from across the gulf of interstellar space. These particles we call cosmic rays. Here we see their tracks in a cloud chamber on the Earth's surface. Trapped within our Milky Way galaxy by chaotic magnetic fields, these subatomic messengers are the only sample of matter we have from beyond the solar system. Magnets are essential for sorting out cosmic rays according to their mass, charge, and energy while they are still above the Earth's atmosphere and have not yet been transformed by collision. With instruments such as this, we hope to discover the origin of cosmic rays and learn something about the birth of our universe. When the magnet is cooled to a mere 4 degrees above absolute zero, it can operate indefinitely without external power. Low power consumption is a necessary refinement for spaceflight or even balloon flight. Such powerful magnets and their electronic particle detectors have not yet been flown in space, but numerous balloon flights have proven the feasibility of doing so. One peculiar problem which must be solved first is the alignment of the magnet with the Earth's own field. In balloon flight, this is an advantage. The magnet stabilizes the balloon gondola until it is turned off by radio command at the end of the flight. Finally, the payload is separated from the balloon and returned to Earth by parachute for further use. But in the space shuttle flights of the 1980s, a strong magnet trying to align the whole spacecraft with the Earth's field could be quite a nuisance. What can be done to keep the magnet from controlling the spacecraft attitude like the proverbial tail wagging the dog? The solution adopted by the designers can be guessed from this shot, which you saw earlier in Skylab. The answer? 2 magnets, a pair of opposing coils with their current flowing in opposite directions. This nearly cancels the magnetic field far away from the coils and minimizes the alignment problem. Space Shuttle will allow countless new experiments in basic and applied science. Many of these will involve magnetic effects, since electromagnetism is one of the fundamental forces of nature. And I expect that some of you will have the opportunity to work on experiments in this new weightless laboratory in orbit above our Earth.